All right, it's time to talk about sequences. Okay, and this will get us closer to ideas related to calculus, including limits especially. So let's talk about what a sequence is, right? So what's our definition here for a sequence? It's just an ordered list of numbers. Okay, so a sequence is an ordered list of numbers. Let's say A1, A2, A3, and so on, abbreviated in the following way. So I'll usually write something like in braces, A sub n, with n going from 1 to infinity. All right. You know examples of sequences, but we should write some down. So here are some examples. Let's say that we have an is equal to n over n plus 2. Okay, and that's going to be n equals 1 to infinity. You can certainly change start index and things like that. If you start at n equals 1, then we're dealing with the sequence a third, then 2/4, 3/5, and so on. What's another example of a sequence? Say n equals 1 over n squared. I'm not writing the braces or the start index here just for brevity. But there's an example of a sequence. What else have we got? Let's say something like the reciprocal of that in example 2. So n equals just n squared. What's another? Let's say an is equal to the root of 4n plus 1 over n plus 1. Okay, so these are all examples of sequences. We can work out some of the first few terms, etc. What we're really interested in when it comes to sequences is what are their limits. Okay, so finding limits of sequences. We're talking about the following question. What happens to a sub n when n gets large? Okay, so that's the question we want to really be thinking about. So what we want to say is something along the lines of the following. So for example 1 that we see above, you may have calculated a limit like this in the past in a calculus course. The limit as n goes to infinity here should be 1. But what does that mean? We want to say something like this. The terms an get closer to 1 as n gets large. And how do we make this more precise? When we talk about closer to 1, there's this question of how close. Okay, and we're going to use the symbol epsilon to denote this closeness. And then when we say as n gets large, there's this question of, well, how large? And here we're going to use this symbol of capital N to denote this largeness in the index. Okay, so those are the two pieces of making the definition of the limit of a sequence precise. Okay, when we say the sequence is getting closer to the limit, how close is it getting? That's going to be epsilon. And when we say, well, this happens as n gets large, how large is n getting? That's going to be capital N. All right, let's write down the precise definition of the limit of a sequence. All right, so a sequence a sub n converges to a limit L if the following is true. If for any epsilon greater than 0. Remember, epsilon is measuring this closeness between the terms and the limit. If for any amount of closeness we want, any epsilon greater than 0, there exists a capital N such that if little n is greater than capital N, we have that the difference between the terms and the limit is less than epsilon. Okay, so the idea here is that capital N is saying, okay, once you get this far out in the sequence, right, if you're that far or further, then you're going to be within epsilon of your limit. And epsilon can be anything, so we can ask to be as close as we want. And this has to be possible. For every epsilon, we find the corresponding capital N. So that's something to keep in mind too, is that epsilon is normally defined first, and then capital N can be defined based on whatever epsilon is. Let's deal with the sequence we were just talking about, the first example we wrote down. So the proposition is the sequence a sub n equals n over n plus 2 converges to 1. Oh, I didn't write down the divergence. Sorry. So at the very end of the convergence definition, if that is not true, the sequence diverges. Sorry. Okay, so back to proving that n over n plus 2 converges to 1 using this definition that we have. So the important part of this is we have to do some amount of scratch work. I'm not sure how this would be possible otherwise. So the idea normally is to work backwards. So we say what we want. So we want a sub n minus L less than epsilon. For us, a sub n is n over n plus 2. Our L, our limit should be 1. We want that less than epsilon. So the question for us is, what has to be true about n to guarantee this is true? Okay, so this is how we're working backwards, is we have what we want to finish with, and then now we ask ourselves, okay, what has to be true about n to get here? Okay, I'm going to do a couple things. N over n plus 2, this fraction is less than 1. Okay, so when I take absolute value here of this difference, what you get is the negative of what's inside. You actually get 1 minus n over n plus 2. So I'm just going to write that. Right, we're assuming n starts at 1, so n over n plus 2 is always going to be positive. If I look at this absolute value of a negative number, which is what I have written in absolute value right there, it should be the negative, which means I can just swap the 1 and what it's being subtracted from. Okay, and then we get this instead. So now I'm just going to try to solve for n. Right, so here I can say, okay, multiply by n plus 2. Okay, if I multiply everything by n plus 2 here, I get the following. Okay, so let's distribute on the right. So now on the left, it's just a 2. On the right, it's epsilon n plus 2 epsilon. Okay. And what was I trying to do? I was trying to solve for n. That's right. Okay, so if we solve for n here, we're going to get 2 minus 2 epsilon over epsilon should be less than n. Okay, what we were looking for was a capital N. We wanted some value that n has to be greater than to guarantee that we get this an minus L less than epsilon in absolute value. And this is the thing that we're going to call capital N, right? We have something of the right form. Little n is bigger than some value should get us to the desired result. So this is our capital N here. Okay, so we worked backwards. We said, what do we want to finish with? What do we have to know about little n to get there? Little n has to be greater than this value. And that's exactly how the definition of convergence and the limit is set up there. So we're armed with this information. So now let's go back and let's go back to our proof of the fact that that n over n plus 2 converges to 1. All right, so we did our scratch work. Here's our proof, right? N over n plus 2 converges to 1. Okay, so the way this starts is to say, well, okay, let epsilon be greater than 0. This is how close we want our sequence to get to 1. Okay, so epsilon can be any positive number, literally anything. It can be 1 over a million, right? It can be a 0 point, a billion zeros with a 1 after that, right? Right. So I guess that's what 1 over a billion and 1. But oh wait, no, not quite that. 1 over 10 to the billion and 1. In any case, epsilon is some positive value that tells us how close we want our sequence to be to our limit. I need to tell you how far to go out in the sequence so we get that amount of closeness. Okay, so I'm going to define capital N based on epsilon, and I'm going to use exactly what we said. I'm going to say that it's 2 minus 2 epsilon over epsilon. Okay, so that's whatever capital N is going to be. I guess here I should require something like epsilon has to be a certain smallest to make sure that capital N is actually going to be positive. But I think this is still okay here. So let capital N be this number that we found in our scratch work. Now what can we say? Okay, what happens if little n is greater than capital N? Then the absolute value of n over n plus 2, our sequence formula, minus 1, which is the limit. So that's the distance between n over n plus 2 and 1. We want that to be less than epsilon, right? We want to show that that this guarantees that value is less than epsilon. Like I said before, n over n plus 2 is smaller than 1. So in absolute value, this expression is 1 minus n over n plus 2. Okay, let me do some rewriting here. I'm going to get a common denominator. So n plus 2 over n plus 2 replaces the 1 minus n over n plus 2. Okay, when we do this subtraction, we end up with 2 over n plus 2. All right, and now we're saying that little n is greater than capital N. So if we plug capital N in instead of little n here, we get a smaller denominator. A smaller denominator, which makes for a larger fraction. Okay, so remember, the thing I just did here was smaller denominator equals larger fraction. So that's how I know that 2 over little n plus 2 is less than 2 over capital N plus 2. Okay, what's 2 over capital N plus 2? Well, capital N was 2 minus 2 epsilon over epsilon. All right, let's simplify here. I'm just going to multiply numerator and denominator by epsilon. So 2 epsilon up top, 2 minus 2 epsilon plus 2 epsilon here. The goal is to get epsilon, and we're getting there, right? We've got 2 epsilon over 2, and that's epsilon. Okay, so we've found a capital N so that if little n is bigger than capital N, the difference between our sequence and 1 is less than epsilon. So this is saying no matter what epsilon you give me, no matter how close you tell me we have to get to 1, I can tell you how far to go out in the sequence to get that amount of closeness. Here's an example. Oh yeah, so we're done. So n over n plus 2 converges to the limit 1. We're done. Here's an example just working out exactly what the numbers are. So for instance, if we wanted n over n plus 2, right, our sequence to be within, say, 100th of 1, that's how close we wanted to get to our limit, then we're going to let capital N be equal to 2 minus 2 times that closeness value, right? 2 times 1 over 100 divided by 1 over 100. Okay, that was our formula for capital N. So this is going to be what here? 200 over 100 minus 2 over 100 is 198 over 100 divided by 1 over 100. That's 198. Okay, so what we're saying then is, so check this. If n is greater than 198, then n over n plus 2 will be within 100th of the limit, which is 1. So the point of our work here is we're sort of playing this game. It has to be that no matter what epsilon, no matter how much closeness we desire, we can always find the corresponding capital N to tell us how far to go out in the sequence to get that close to the limit.